So good afternoon. Shortly, we will hear an interesting lecture by Element 6 experts on the synthetic diamonds for the photonics industry. This webinar is part of an enlightening series organized by Photonics Israel, exploring diverse facets within the field of photonics. Photonics Israel is sponsored by ISORAD and work in close cooperation with its subsidiary, the Israeli Center for Advanced Photonics. My name is Shlomo Glaser, and I'm the manager of Photonics Israel. The lecturer in this webinar are Dr. Ian Frail, the Business Development and Program Manager at Element 6, and Mr. Michael Persson, the Head of CVD Commercial Application and Commercial Development at Element 6, and Dr. Matthew Markham, the Head of Quantum Technologies at Element 6. Question and answers will be at the end of the lecture. Please post your questions on the chat tab. I wish you all a pleasant and useful listening. Ian, Michael, and Matthew, the stage is yours.
Okay, thank you very much, Shlomo. Thank you for the introduction, and thank you for this opportunity to present this webinar to the photonics community in Israel. We have quite a lot to cover, so I am going to jump right into our presentation. So I'm going to go into full screen mode, so hopefully you can see all that clearly. So as you see on this page, the title of our webinar is Synthetic Diamond for the Photonics Industry, Needs, Technologies, Challenges, and Applications. Just to remind everybody that please don't copy and redistribute this. If you do want some slides afterwards, please reach out and we'll be able to share our slides with you. This is the structure of the webinar that we are going to give today. I'm going to give a brief overview of Element 6, just to tell you who we are, what we do for those that aren't familiar with our organization. I'm then going to hand over to my colleagues. So Michael Pearson is going to talk about diamond intrinsic optical properties and applications. And then Matthew will talk about diamond materials for quantum technologies. And then at the end, hopefully we'll have 15 minutes. We'll do a brief summary and answer any questions that you guys might have. So Element 6, we are a manufacturer of super hard materials, such as synthetic diamond, tungsten carbide, and cubic boron nitride. We're part of the De Beers group, and De Beers are owned by Anglo American. Element 6 is actually made up of two parts. So there's Element 6 Technologies, which is 100% owned by the De Beers group. That's the part of Element 6 which is relevant to this webinar today, in the sense that the applications and the products that we're going to talk about are based on CVD diamond, which is within our technologies business. The other part of Element 6 is Element 6 Abrasives, and that has a joint shareholding, so that's jointly owned by the Beers Group and by Umicore. On this slide here, this shows a sort of summary of our history. There's a lot of information on here. I won't go through all of this, but I just wanted to point out that we have been around for quite some time. So we were founded in 1946, so we're about 78 years old. So we've been around for a while. In the early days, our products and applications were addressed using the high pressure, high temperature method of growing diamond. And then in the 1980s and 1990s, we developed from scratch our CVD, chemical vapor deposition, diamond capabilities. And as I said, that's part of our E6 technologies, and that's what's relevant to the applications we're going to talk about today. This just gives an overview of some of the areas that we address, some of the industries that we address. So on the top row of this slide, we have some examples of abrasive applications. So these are applications like mining, automotive and aerospace, machining, oil and gas drilling, which utilize the traditional mechanical properties of diamond, so the abrasive hard properties of diamond. On the bottom row here are some examples of advanced applications that we address primarily using CVD diamond. So semiconductor industry, optics, which obviously is today's talk, thermal management. So diamond obviously has a very, very high thermal conductivity. Next generation applications is about sensors and detectors and the quantum applications, which Matthew's going to talk about later, sort of falls under that heading there. The way that we make our products, primarily we use 3 different manufacturing techniques from a synthesis point of view. There's the high pressure, high temperature synthesis technique, where we're trying to mimic the conditions of pressure and temperature under which diamond forms naturally in the Earth's mantle. Cemented tungsten carbide is made by a sintering technique, and then CVD technique for the more advanced applications of synthetic diamond. And then just a little bit about microplasma CVD, which is the type of CVD that we use in element 6. So unlike the high pressure, high temperature, CVD is a low pressure technique. We use a methane hydrogen plasma, so methane contains carbon. That's our source of carbon for diamond growth. It's a very versatile technique. So with one reactor platform, we can grow on flat substrates, curved dome substrates to produce diamond parts of different shapes. We use microwave energy to heat up our gas mixture in order to form a plasma. The gas temperatures are typically greater than about 3000 Kelvin, and we do this in order to create all of the chemical species required for diamond growth. In essence, there are 2 types of diamond that you can grow using this technique from the perspective of the microstructure of the material. But generally, if you grow on non-diamond substrates, you produce polycrystalline diamond. That's what's illustrated in this diagram here. So essentially, we nucleate randomly oriented grains on a substrate. Then you have competitive grain growth, and you form a wafer, a fully dense wafer, which is comprised of diamond crystallites. And that's a great material for addressing the majority of industrial applications that we make. You can produce large areas up to around about 140 millimeter wafers in diameter. And they're essentially just limited by the size of the reactor and the size of the substrate that you use. For many applications, however, you want single crystal or monocrystalline diamond. And to produce this, you need to grow on single crystal substrates. And currently, the sizes are sort of limited to around 5 to 10 millimeters, and that's limited by the size of the substrates that we have available. There is another technique which you can use to produce single crystal diamond called heteroepitaxy, where essentially you grow single crystal diamond on a non-diamond substrate, and you use special interlayers to get the individual crystallites to coalesce and form a single crystal. But I'm not going to cover that today. You can read about it in the literature, and Element 6 and other groups are working on that heteroepitaxial approach. So that's what I wanted to say by way of introduction. I'm now going to hand over to Michael, who's going to talk about diamond intrinsic optical properties and applications.
Lovely, thank you very much, Ian. Yeah, so as Ian said, I'm just going to talk a little bit about the sorts of properties that actually make diamond a very attractive material for certain optical applications. I'll talk a little bit about what those applications might be, and then I'll touch on some of the challenges with integrating diamond into your optical systems. So first of all, why would you want to use diamond for optical applications? We all know diamond's pretty expensive stuff. So what actually gives it a benefit over other materials? The first thing really is it's an incredibly broad transmission spectrum. So diamond is pretty much transparent from its band gap at 225 nanometers all the way through to radio frequencies. It has a small amount of absorption due to phonon band absorption in the sort of 2 to 7 micron wavelength range. But other than that, it's pretty much transparent. Depending on the grade, you might have a bit of absorption in the visible as well, but that's largely down to optically active defects, so nitrogen-containing defects. There are other impurity atoms that you can get in your diamond, but we're able to control those very well in the CVD diamond that we grow. So if you need them not to be there, we can achieve that. Comparing that to other sort of traditional optical materials, you can see a comparison of some common optical materials in the graph and on the top right there, and you can see that diamond really does excel in the broad nature of its transmission spectrum. The next thing that is very often important in optical applications is the high thermal conductivity of diamond. Diamond has, certainly our optical grade diamond has a thermal conductivity that is in excess of 2000 watts per meter Kelvin. For those of you that aren't used to thinking in terms of thermal conductivity values, the graph on the bottom right gives a useful comparison between some other common materials used for optics against diamonds. So typically optical materials will have thermal conductivities in the sort of single digit or tens of watts per meter Kelvin. And as I said, diamond, optical grade diamond, we're in excess of 2000 watts per meter Kelvin. Just for a bit of further context, copper, which we would typically use for heat spreader applications, heat sinks, would consider it to be a very good thermal conductor. That has a thermal conductivity of about 400 watts per meter Kelvin. So diamond is still blowing copper out of the water in terms of its thermal conductivity. Why does that become important? Well, if we think about, for example, optical coatings, if we took a piece of zinc selenide, which is typically used at 10.6 CO2 laser wavelength, and we compare that to diamond, which is also often used at 10.6 microns, both of those materials will need an optical coating in order to get the high transmission values that you require for your application. In the case of zinc selenide, if we have small amounts of absorption in the optical coating, the very low thermal conductivity of the zinc selenide means that heat takes a long time to get out of the coating, and it leads to high peak temperatures in your optical coating, which can lead to premature failure. In the case of diamond, its very high thermal conductivity in the diamond substrate means that it can spread the heat that is from any absorption in your optical coating, and that reduces the peak temperatures achieved in your optical coating, which in turn can lead to things like improved LIDT for your optics. So it really comes into its own for high power optical applications. I've just talked a bit about LIDT, so laser induced damage threshold. The diamond substrate itself typically has a very high laser induced damage threshold. The limitation is often the coatings, which I'll talk a little bit about in the challenges later on. Diamond also has a very high Raman gain coefficient, so this is potentially useful in applications where we perhaps want to shift an easily achievable laser wavelength to a wavelength that is less easy or not possible to achieve using conventional laser sources, or we can only achieve it with dye lasers, for example, which are costly and bulky. So it's potentially a solid state route to unusual wavelengths. And then also, high mechanical strength is sometimes important if we have, for example, a window trying to hold off vacuum, which is quite common in some of the sort of CO2 laser applications. A diamond window can be a lot thinner than a zinc selenide window, for example. Also of interest, perhaps less for laser windows, but high resistance to thermal shock. So in situations where there might be a sudden high heat load on a window. So for example, you could use diamond for a missile dome end. If that gets very hot very suddenly, diamond is unlikely to fracture as a consequence of thermal shock, because the thermal conductivity is so high in the diamond. Low dispersion, so this is talking about the rate of change of the refractive index with wavelength. So for diamond, the refractive index is broadly constant for a large range of wavelengths, and this is potentially useful for things like multispectral imaging. And then the final point that I wanted to make, it's not really a property of diamond, but it's more what we're able to do with diamonds. So element 6, we have technologies and processing capabilities that allow us to very carefully control geometries. So an example of that is attenuated total reflection prisms, which are used quite extensively in FTIR spectroscopy, for example. And the tolerances on the angles, on the dimensions of those prisms is very exacting. They don't look as impressive or as pretty, perhaps, as a round, brilliant cut diamond for jewelry, but the tolerances that you work to on these prisms is much higher than for any gemstone. Also, things like parallelism and flatness. Of parallelism on our Raman crystals, we achieve to less than 0.1 of a degree on the parallel end faces through which the laser will pass. And routinely we achieve flatness on large diamond optics, so 50 mil diameter optics of less than 1 fringe at 633 nanometers. So we're able to achieve very high flatnesses over large area parts. Could I have the next slide, please, Ian? Thank you. In terms of applications, I've already touched a little bit on high power laser optics. So a good example here is extreme ultraviolet lithography. So in order to generate the ultraviolet light that is needed for extreme ultraviolet lithography, a tin plasma is formed, and this is formed through tin droplets coming down into the path of a very high power CO2 laser. Now, the drive laser that generates that CO2 laser to hit your tin droplet has a number of diamond windows in it, and the reason we're using diamond in that application is for the thermal management and the high transmission at 10.6. So we've talked a bit about zinc selenide. It's really that application where the coating absorption can only be managed using a diamond window. Alternative materials just won't cope in that very extreme environment. There are other semiconductor processing applications, 10.6, also 1064 nanometers for annealing purposes, for vias, things like that, that diamond optics are used. I talked a little bit about multispectral imaging. Again, the low dispersion and the broad transmission spectrum of diamond mean that you can image at a number of different wavelengths using the same window. It reduces size, complexity. Perfect. Yeah, it's sharing in, I think, just in presentation mode, and then brilliant. Right, I'll crack on. Excellent. So where was I? I think I was talking about multispectral imaging. Again, not much more to say there, except for yeah, we can image multiple wavelengths all through the same window, which has potential uses. Extreme environments. So again, if you're trying to image through, for example, a hot window, if you use a sapphire window for your imaging, for example, you can try and cool your sapphire window, but it's relatively low thermal conductivity. It is going to limit. Oh, it's all dropped out again then. Yeah. At least we're all still here, even if the slides aren't. That's progress, eh?
Yeah, okay. You share the screen now, I believe.
There we
Yes.
go. Yeah, we're back. Yep. Yeah, so imaging in extreme environments. As I was saying, if we, for example, are trying to do IR imaging through a hot window, you reduce your signal to noise ratio. Or you have a poor signal to noise ratio. In the case of a sapphire window, there's not a huge amount you can do about that. You could try and implement a cooling system, but the low thermal conductivity of the sapphire is unlikely to yield much benefit. In the case of diamond, if actually you have well-designed cooling, you can keep your window temperatures pretty low, increase your signal to noise ratio, and get better imaging through that window than, as I say, with other common materials. And finally, mirrors for high power lasers. Again, the high thermal conductivity of diamond means that any hot spots are minimized on your mirror surface. This, in conjunction with a low diamond CTE, means that you reduce the amount of thermal distortion you get out of your mirror, improving your laser beam quality as it comes off of your mirror. That, in conjunction with the low density of diamond and high stiffness, means that you can reposition your mirror very quickly and very accurately compared to, for example, a copper mirror. Next slide, please, Ian. Brilliant. Just a quick note on the differences between polycrystalline diamond and single crystal diamond. So Ian touched on this briefly in the introduction. Just to say that both materials we can produce with excellent transmission properties. We achieve that by keeping the levels of absorbing defects in both the polycrystalline and the single crystal material to very, very low levels. The main differences, I would say, are it depends on what wavelength that you're working at as to whether you want to use polycrystalline or single crystal material. On the right hand side there are examples of two different grades of single crystal diamonds. So our standard single crystal CVD grade and our low absorption optical grade diamond. If I were to overlay polycrystalline diamond on that, what would I expect? I would expect less transmission in the in short wavelengths, so in the visible, for example, and that's not actually absorption that's going to be causing that. It's predominantly scatter. And that scatter is a consequence of things like grain boundaries and other very small defects that are present in the polycrystalline material. If your application is actually at a relatively long wavelength, so 10.6, I've talked a lot about that CO2 laser wavelength. The difference in performance between your single crystal and your polycrystalline materials is going to be very minimal. And just to give you a sense of what sort of scatters we'd expect. So for polycrystalline material at 1064 nanometers, we'd expect typically about 2.5% scatter. For our single crystal grades, that'd be down to about 0.7% scatter. But if we then have a look at our polycrystalline material up at 10.6 microns, we're expecting scatter down as low as about 0.5%. So pretty low. And the reason for that scatter, as I said, is a combination of grain boundaries. Also, birefringence in polycrystalline material is typically quite high, which leads to a lot of scatter at shorter wavelengths. And then also the surface quality that we're able to achieve. So single crystal diamond, we're able to achieve surface finishes of less than 2 nanometers RA. So very, very smooth surfaces. Polycrystalline material, we're still achieving very, very smooth surfaces, but typically we're able to achieve less than 10 nanometers at a sort of best effort on an optical grade polish. Next slide, please, Ian. Brilliant. And then just touching on one of the challenges of working with diamond. There are a few, but I really just wanted to focus on optical coatings. So these can be tricky to get right on diamond. Why? I'd say for me, it's three main contributing factors. So one is adhesion of the coating to diamond. The diamond surface is typically pretty chemically inert. If we were to try and braze a piece of diamond to another material, we'd typically put a metallization on that consisted of a carbide forming element, so titanium or chromium, for example, which forms a very strong bond with the diamond. When we're talking about optical coatings, we often can't do that. We're quite limited in the materials that we can use because we need the optical performance. So adhesion can suffer as a consequence. Surface preparation, again, certain ways of cleaning the diamond can lead to surface modification, which can in turn lead to surface absorption. So we've got to be careful of that. And then diamond's very low coefficient of thermal expansion means that once you've got layers on top with different coefficient of thermal expansion, that system can be quite sensitive to increases in temperature, which are typically what you get when you have a small amount of absorption in a coating layer on an optic. So these things really make it quite a challenge. That said, we do have a lot of experience working with partners, and you know, recently and over the last sort of 10 years, we have produced a range of coatings, everything from single wavelength anti-reflective coatings to dual wavelength anti-reflective coatings, broadband, high reflectivity coatings, beam splitters, and bandpass filters. So we do have experience, but typically, if you want a new or slightly unusual coating, there is a period of development that is needed in order to optimize the coatings to your application. The other thing that I'd just like to highlight is you can achieve good anti-reflective properties with an all diamond solution. So if you structure the surface of the diamond, so a moth eye type structure as is shown on the right hand side of the slide there, you can achieve pretty good transmission. So maybe up to sort of 97–98% transmission. That particular structure is for 10.6 microns, which is a product we've made historically. And the benefit of this system is that your LIDT is much higher than for traditional dielectric coatings. So if you can take a small hit on spectral performance on your transmission, then you can achieve much higher LIDT threshold using either a structured or a random surface structure AR coating. Yeah, and the final thing, just to say that the image in the middle there is a good example of when coatings go wrong. So this is a Raman crystal that has been coated on its end faces with an anti-reflective coating. The direction of the laser in this image is from the left-hand side to the right-hand side, and you can see that what's happened in this case is the coating has failed on the left-hand surface. That's caused an absorbing feature on the surface, and then the laser has drilled through the diamond, creating a long extended graphitic hole in the diamond, which is absolutely not what we want. So it's important to get these things right, and when we don't, it can lead to issues such as that. Brilliant. I think that's all I want to say, Ian. I'll hand it over to Matthew.
Cool, thank you, Michael. So now for something a little bit different. So just a reminder, I'm Matthew Markham, Head of Quantum Technologies here at Element 6. And so now we're going to move on to talking about diamond more as an active component in optical devices, and specifically quantum devices. So if you can go to the next slide, please. So why is diamond an interesting quantum material? It all comes down to specific properties around defects in the diamond material, and these are defects that are actually you want, and these defects behave effectively like trapped atoms inside the diamond crystal lattice. And what's really key about these defects is you're able to manipulate the quantum properties of these defects. So the specific quantum property we're talking about here is the electronic spin associated with these defects, the most common one being the negatively charged nitrogen vacancy defect. And it's this defect which is actually responsible for making synthetic diamonds the pink color as shown on the left here. And why diamond is such a good material for this is effectively the diamond crystal lattice doesn't really interact with this spin. So whilst the diamond itself is at room temperature, the sort of temperature associated with the spin is actually a sort of microkelvin. So you've got this good separation between the quantum properties and the host material, which is diamond. The second important point about diamond defects in diamond for quantum application is they're very easy to manipulate. So the nitrogen vacancy defect, you can control the spin simply by shining green light onto it and microwaves, and that allows you to put it into states called things superposition, or create entangled states between multiple defects, and that's very simple control. And as I mentioned, you can do this at room temperature. So you've got all these quantum properties which allow you to do these things at room temperature. The control mechanisms, the light and the microwaves, they're all very simple things to apply, which means you can create a very simple device that operates at room temperature, allowing for low size, weight and power devices to be developed. If we go to the next slide then, Ian. So the types of devices you can be developed, there's a number of them, and I'll just briefly talk through them and then the application to the different segments that they apply. So the highest TRL, so the technology readiness level devices, are magnetic field sensors, and there's sort of 3 different modalities of this. There's something I call bulk magnetometry, which is effectively where you're just interested in the magnetic field, the total magnetic field, with very little spatial resolution. So you're just using the whole diamond to sense the magnetic field. Then you've got wide field magnetometry, which is essentially where you're starting to be interested in some spatial information. So you're talking typically on the micron type scale, sensitivity. Spatial sensitivity, spatial area resolution. And then you've got nanomagnetometry, where you're using single defects, so single nitrogen vacancy defects, to detect magnetic fields on the nanoscale. You also have a number of other sensing modalities. I'm not going to go through them all, but things like temperature sensing and electric field sensing, as well as the ability to detect RF fields as well. So there's a number of different sensing modalities. Then you've also got the more traditional sort of quantum type applications, so things like quantum computing and quantum communication. And lastly, you've got other applications such as gyroscopes and masers. So all these things are sort of being developed using diamond as this platform material. and they feed into a number of different market segments. So on the right here, I've just got sort of some examples, but obviously you've got things like healthcare, you've got things like defense, you've got things like material characterization. So there's a number of different areas that these technologies can be applied. And what's exciting at the moment is there's a large number of academic groups, probably around at least 400, probably a lot more around the world, developing diamond-based quantum technology, but also now a lot of companies. So there's roughly 60 to 70 companies worldwide now developing diamond-based quantum technology. So we're really seeing this sort of being pulled through, which is quite exciting. So we're going to the next slide then, Ian. So what does a diamond quantum device actually look like? So I mentioned earlier, it's actually a relatively simple device, as we've shown here on the left. So you just need a green light source. So here I've described it as a laser, but it can be an LED. It's not that fussy, to be honest, about the laser source. That then shines onto the diamond containing these defects. You then apply an RF field at 2.8 gigahertz. That's sort of a similar sort of frequencies to what your mobile phone is operating at. You apply a static magnetic field, and then the green light basically stimulates this red photoluminescence. So you need a filter because you're just interested in measuring the red photoluminescence. That's your signal, and so that peaks around sort of 650 nanometers. So that means you can use a silicon photodetector. So that's another quite advantage of a diamond-based quantum device, is that all of these are relatively easy to get. Nobody's using some detector in a wavelength range where there are detectors or lasers where you haven't got the right sort of color. So it's relatively easy to build a device, and whether you're building a quantum computer or a magnetic field sensor, the basics are the same, although admittedly in a quantum computer generally it's a lot more complicated. Okay, so that's the system. On the right here, I talk about the material choice depends on the device design. So in the center, I've got three properties that relate to the diamond. So T2 star, so this is the spin lifetime of the NV defect. So you want that to be as long as possible. NV minus emissions, that's the light coming from the defect of interest. You want that to be maximized, whilst the other red luminescence to be minimized. And the diamond geometry, so how the light is going to bounce around the diamond, how the light's going to be extracted from the diamond. Now, when actually choosing the right diamond for a quantum device, actually you need to think about how you're building the system. It's really a system problem. That means, how are you going to extract the light out of the diamond? How are you going to detect the red light coming off of the NV defects, and how are you going to apply the microwaves? So therefore, we've developed different materials to allow us to address different sort of device designs. So if we go into the next slide, Ian. So on the left here, at the top left, I've got three different types of materials that we currently provide commercially. So on the far left, we've got our electronic grade diamond. So this is basically a very high purity diamond. So it's parts per billion in terms of nitrogen concentration. So what this means is you can use it to detect, measure single NV defects. So the nanomagnetometry example I talked of earlier uses this type of material to create single defects. You can also implant other defects into it. So there are, I've mentioned mostly the nitrogen vacancy defect, but there are other interesting defects, and people use our electronic grade diamond to implant these different elements into electronic grade diamonds and create other defects. And then we've got what we call the DMV series, which is basically addressing these sort of sensing type applications where you want a higher NV content material. So we have two different grades here. We have a B1 grade and B14, where effectively the number relates to the nitrogen concentration in the material. And the reason we have two different grades is, as I said earlier, your device design depends on the material of choice depends on your device design. So some devices designs will prefer a B1 will be better, and some device designs a B14 would be better. But we don't just do these commercial materials. In my team, we do a lot of development work and produce another range of different materials. So the first one here in the research and development box on the right, we have a material where we produce a very thin layer of NV containing diamond on top of one of our electronic grade diamonds. And this allows you to do some of the imaging magnetic field sensing I spoke about earlier. And then in the middle we have other range of bulk diamonds containing a range of different nitrogen concentrations. And then on the far right, we have a carbon-12 high purity material. So it's akin to the electronic grade diamond, but this time we've removed the carbon-13 you get in the material, and this improves the spin decoherence time. So if you go to the next slide. So I'll just talk you through a few example applications. So the first one here is a magnetic field sensing application. So this is a project that we've been doing with Lockheed Martin. And so what they're doing here is trying to make a denied GPS system. So this is based on the fact that if you can measure the magnetic field from the Earth's crustal magnetic field, you can actually position where you are on the Earth. And that's what this image on the false color image on the top right shows you. It's a digital map, magnetic anomaly map showing the variation in Earth's field. So if you know the strength and the direction, you can work out where you are on the Earth, and you're not reliant on a satellite. Now, this obviously feeds into another big advantage of diamond in that it is a true vector magnetometer. So the fact you're using a diamond with a crystal lattice, you've got 4 different orientations of the nitrogen vacancy defect, and that allows you to actually extract a true vector signal. So what Lockheed have done is they developed this prototype system at the bottom right here with the dimensions as highlighted there, which obviously can be in principle shrunk down even further to make this low swap device, which is then deployable on a range of different platforms. So if we go on to the next example, which is also another magnetic field sensing application, but this time it's an imaging modality. So in the image on the top of the diagram, what we're showing is we have a very thin layer of NV containing diamond, but instead of just having a silicon photodetector, we actually have a CCD, and now that gives us spatial information. And so what this company that we've been working with called QDTI, they're based in Boston in the US, are looking to develop a healthcare application. In this application, what they're doing is looking to detect proteins. And the way they do that is by using magnetic beads which attach to proteins, which is in the image in the bottom middle. And when you've got a particular type of bead, they call them A bead and B bead, attached to a protein, that then registers itself as a signal which they'll see in their device. And the advantage of this, it gives you much quicker turnaround than traditional methods to do proteomics, and also you can use much lower amounts of material. And this is particularly important for things like traumatic brain injuries. So when you're having a TBI, you express particular proteins, and those proteins can give you a good indicator of how your body is healing. And even though you might feel okay, if you still got these proteins being expressed, that means actually your body's still recovering. So having a quick mechanism to feed this back is critical. So going to the next application. Okay, so I will just do this last one, which is, so I'm just realized I'm running out of time. So quantum networking, is another application. This is obviously more quantum, very much using the quantum properties of diamond. And the advantage here is basically diamond makes a very nice quantum node. What that means is in quantum communication networks, what you want to be able to do is send single photons along fiber optic, but obviously photons will get absorbed. And unfortunately, due to the fact that you can't copy quantum information, so you can't put in a traditional repeater like you would in a normal network where you just put an amplifier in, you can't do that. You need a mechanism to repeat, or a different way of repeating information. That's done through a process called entanglement. And diamond qubits have a very high entanglement rate, which allows you to do this at a level where you can make these networks work. And there's a number of examples now of this being demonstrated both in the Netherlands and Boston. So Diamond acts as a very nice material platform to do this. And I think it's also worth highlighting the fact that that a lot of the technology that's been used to develop this also allows you to process diamond in different ways. So that image there in the middle there shows a photonic crystal fabricated using ICP etching. So you can make some very intricate structures. So now, Ian, if we go on to the summary slide then. So hopefully we've shown you some of the different things that Element 6 does for diamond photonics. With you basically taking advantage of diamond's range of different properties, whether the optical, thermal, mechanical properties, as well as the sort of quantum properties. And I think key to our business is really very much working about in partnership with people. So really, it's the way we succeed is basically finding partners that are interested in developing diamond solutions and working closely together with them to making sure that we can provide a full diamond solution. So I think we're at the end of our time, so I'm happy to take any questions. And Ian, I don't know if you want to leave the last slide up there, just with your details. If you've got any further questions, you can speak to Ian and we can take questions if there's any in the chat.
All right. Thank you very much, Ian, Michael, Matthew, and Hodaya. Now it's the time for the audience to challenge the Element 6. So please.
I can see there's just one question in the chat about in the graph presented on page 12. Is the graph presented on page 12 based on diamond coated with ARC, which I presume is an anti-reflective coating? So the answer to that question is the graph on page 12 was actually a graph of absorption coefficient. So I don't know exactly where that data has come from, but I very much suspect that won't be anti-reflective coating. It'll just be a UV-vis absorption measurement of an uncoated piece of diamond. So it's really absorption coefficient rather than transmission in that graph.
I think it's also corrected for reflection losses as well.
Exactly. Yeah.
I have a question. I have two questions. Is it okay? Do you hear me?
Go for it.
Yeah. The very first, do you have any numbers about birefringence as windows or as materials that the light passes through at the various kinds of diamond? That if you have that's question number one. And I had another question that I wanted to ask. Yeah, about your AR coatings. Sometimes you have to have a very wide range of AR coating. It means you use a laser, whatever, in the mid IR or in the far IR, as well as something seen in the visible or things like that. And is those designs already somebody is kind of using it, doing it with a very wide range? Because normally the lambda quarter or whatever that you put on top of it is a very big difference between 1 micron and 10 microns, so half a micron and 10 microns.
Yeah, good questions. So just on the AR coatings first. So there are customers that are using both broadband, not as broad as you described there, so not anti-reflective from 1 micron up to 10.6 or even mid IR. But there are customers who are using dual band anti-reflective coating. So if you've got, for example, 1 micron and 10.6, there are customers who are using those, and we do have partners who are capable of doing those coatings to a high quality. I don't doubt that other dual wavelength anti-reflective coatings are possible. And we also have produced broadband anti-reflective coatings Though again, the range. So, for example, off the top of my head, I know that we've done coatings that are sort of 10.2 to 10.6, for example. So, reasonably broad, but not spanning multiple microns. And the final point there is I talked about the sort of moth eye type anti-reflective coatings. Those typically have quite good broadband capability, so they will give you an anti-reflective effect over a number of microns in the infrared. It won't be as good an anti-reflective effect as you would get from a dielectric coating typically, but that broadband effect is definitely there. On birefringence, it's you asked what are the typical birefringences of our windows. I'd struggle to give you any definite numbers off the top of my head, but as I mentioned, our polycrystalline material typically has high birefringence, and the reason for that is when you get this competitive grain growth, you get a lot of intrinsic stress that builds up in the individual grains, and it's that stress that leads to strain in the lattice, which is what causes your birefringence. So polycrystalline material typically has high birefringence, and that's one of the main contributing factors to the high scatter at short wavelengths. For single crystal products, we do have methods of controlling birefringence to very low levels, and that's particularly the case in, for example, our Raman crystals, and generally our optical grade single crystal materials. Off the top of my head, and Ian, correct me if I've got this number wrong, but I think 2 × 10⁻⁶ is the number that we would normally.
5.
2 × 10⁻⁵. Thank you. I'm glad you corrected me there before I get people's hopes up. But that's still a very low birefringence in that material.
Can I chime in with a question, please?
Yeah, of course.
Yeah, well, right. First of all, thanks very much for a very insightful and educational presentation. I've got 2 questions, if I can do that for the price of one. My first one is for thermal management applications. You've got polycrystalline grades such as TM220, which is marketed as having also very high thermal conductivity in excess of 2000 meter per Kelvin. And that I think that there is not much of a difference between that and single crystal diamond. Would you say the benefit of a single crystal is primarily in the optical domain? Is there any thermal conductivity benefit to be had by switching to single crystal from polycrystalline?
Yeah, good question. So I would say, broadly speaking, at the moment, what's the advantage of polycrystalline over single crystal, for example? Polycrystalline is available in larger areas, thicker, and at lower cost than single crystal diamond. In terms of absolute thermal conductivity values that are attainable with polycrystalline material versus single crystal, there's not really much difference. I would say the single crystal, really it is for the shorter wavelength applications where you're going to see a significant benefit. What I would say is if and we are seeing applications that would potentially benefit from thermal conductivities that are even greater than 2,200 watts per meter Kelvin, which is what we would typically specify for our optical material, for example, or for our single crystal. That is achievable through some of the isotopic enrichment growth that Matthew actually spoke about as being beneficial for quantum applications. Using that isotopic enrichment, you can actually reduce phonon scatter in your lattice, and although it's very difficult to measure, and I'm not sure anyone has actually measured it, the modeled results suggest that you should be able to get thermal conductivities up to about 3,000 watts per meter Kelvin. Now, you wouldn't necessarily want to do that for a bulk piece of diamond, but for capping layers, for getting an immediate heat spreading effect where you've got a particularly hot spot on a electronic device or a coating, that might be a beneficial arrangement.
Okay, thanks very much for that. And my second question is going back to anti-reflection coatings. You mentioned multi-patterns. I'm just wondering if these are meta surfaces or some kind of diffractive optical elements that create an anti-reflective effect. And are you aware of anyone putting down such patterns in the near infrared to create an effective diffraction coating by simply a shallow etching of a microscale pattern? Mm-hmm.
Yes, we've worked with a few different partners on structured coatings. I say structured. We actually the image that I showed was of a surface structure for 10.6 for CO2 laser optics. As I say, that's structured pillars which are giving the AR effect. We've worked on similar structures for shorter wavelengths, so more for near IR. The challenge is, as you get shorter and shorter, that your structures have to become smaller and smaller, and controlling feature size becomes more challenging, but it is still possible. We've also worked with partners on random AR coatings. So these are unstructured metasurfaces that still give a very significant anti-reflective coating. So instead of pillars, you've got a random structure on your surface. But as I say, it still gives you perhaps not as good a total AR effect, but it gives a very cost-effective way to achieve a very significant transmission increase.
Right. Okay, thanks very much for that. Cheers.
No problem.
Gadi, are you do you have some questions? Well, maybe all of the talks gives the answers to the people. But this is a great chance now to ask questions and to maybe to put some to start some way to be in contact with element 6. So the stage is yours, audience. Rafi. Okay, all right. So maybe later people start digest this information and come to you later.
Yeah, well, I would just say that you can follow us on LinkedIn. So we have obviously we'll post stuff that we do as a company, and I think you can follow me in and the things that we do on there. So if you're interested or you want to come back to us, yeah, we're easy enough to find.
All right. So I would like to thank you again for these interesting lectures, and I hope that we'll succeed with the diamonds. So thank you very much.
Thanks for the opportunity.
Thank you all. Thanks.
Yes.
Okay. Thank you. Bye.
Bye.
Bye-bye.
Thank you a lot.
Thank you.